Well, my topic is a GOSAT, and it's a satellite to make measurement of the greenhouse gases globally. And so, as already you know, in February 2005, the GEO's 10-year implementation plan was adopted at the Third Earth Observation Summit in Brussels. And climate is one of the most important issues in the GEO's plan, and satellite is one of the most innovative technology among the tools for Earth observation. It is a major component to promote GEO's plan, and it has been developed rapidly for the past several 10 years. And Japanese major tasks for GEOS include GOSAT and DS. And GOSAT, Greenhouse Gases Observing Satellite, Ibuki in Japanese, is a satellite to observe carbon dioxide and methane, and it was launched in January 2009. DS, Data Integration and Analysis System, is a database to utilize a huge amount of Earth observations data, including satellite data. So today, I'd like to focus on GOSAT and DS as a Japanese contribution to GEOS. What is GOSAT? I do not expect anyone here knows the name, but most of Japanese don't know either. Unfortunately, it is not as popular as Japanese comics manga. So listen to my story anyway. And GOSAT is the first satellite that is dedicated to greenhouse gas monitoring. Targets of GOSAT are carbon dioxide and methane. The onboard sensor is named Tanso FTS. FTS means Fourier Transform Spectrometer. That is very innovative technology as a sensor in space. For the past long years, carbon dioxide measurement from satellite has been regarded to be almost impossible. That's a crazy idea, they say. But now we all know it is possible. Many validation studies revealed enough reliability of GOSAT data. I believe that was a great step toward a new age of global observation of greenhouse gases. GOSAT has collected data for more than 6 years as of 2015, and this figure shows the trend of carbon dioxide observed by GOSAT for these 6 years. The essential merit of satellite observation is wide spatial coverage, and the current ground-based observation network is like this. In some areas, only limited number of the data are available. The advantage of GOSAT is its wide spatial coverage. This kind of global data can bring us an important information on distribution of source and sink of greenhouse gases. We can utilize the data of greenhouse gases, whether they are obtained from satellite or ground-based instruments, by putting them into a computer model called atmospheric tracer transport model. So we can improve our first guess of geographical distribution of greenhouse gas flux by adding the information of observation. The output is called posteriori. That is a revised greenhouse gas flux dataset. This process is called inverse analysis because derivation of emission from gas concentration is an inverse process. I will show you an example. This figure shows a monthly estimate of carbon dioxide flux by applying GOSAT data as well as ground-based data. The upper panel shows the observed data, and the lower panel shows the result of emission absorption flux of carbon dioxide in July 2011. And the color indicates monthly mean amounts of the source and sink. The red color shows carbon dioxide emission. On the other hand, green over the land or blue over the ocean shows carbon dioxide absorption. In this case, we found large carbon dioxide emission in India and some part of North America and Africa in this month. In this way, we can now monitor the emission and absorption distribution in a monthly basis, and GOSAT can derive methane emissions in the same way. However, the capability of the satellite is not perfect. There's still a gap between present technology and scientific requirement. First of all, atmosphere is moving around and goes up and down. So therefore, we need to know the three-dimensional distribution of greenhouse gases. However, most of optical measurement from space utilize the absorption of solar light. Therefore, satellite sensors at short wavelength infrared can measure only column abundances of the species such as carbon dioxide and methane. On the other hand, thermal infrared wavelength is not sensitive to the lower part of the atmosphere, though it can measure profiles. I say that the advantage of satellite measurement is wide spatial coverage. However, we cannot see under the cloud, actually. So we have only limited data over cloudy areas, say in Asia in monsoon season, for example. Then we need a great effort to combine short wavelength data and the thermal infrared data, or combine satellite data with ground-based data, and anyway, to get a whole picture of greenhouse gas distribution. Okay, here I'd like to introduce my own challenge. AMASA is a project sponsored by the Ministry of the Environment, Japan. We have two goals in this project. The first goal is to improve methane emission estimate from South Asia. The concept of the project is to downscale the emission estimate from global scale into a regional scale. Our second goal is to develop an emission mitigation proposal. A large part of methane emission from South Asia is from agriculture, mostly from ruminant animals, and some are from rice cultivation. In this project, we are focusing on methane emission for rice fields. One approach to reduce methane emission from rice field is an intermittent draining of water. Another approach is a proper fertilizer management. Based on local experimental works, we will arrange some mitigation scenarios and input the emission scenarios into atmospheric transport model and try to examine if it is realizable or detectable. These are our latest activities. This slide shows atmospheric measurement that we are carrying out in Sonipat, north of Delhi. We are collecting a bottle of air once a week in a pump house of local farmers, like this. And we are doing similar sampling in Kumila in Bangladesh too. In Sonipat, a group of Nagoya University, Japan, is doing a continuous monitoring of ambient methane concentration by applying a laser long-path absorption instrument. This is also a very innovative technology. Where are rice paddies in Asia? This slide shows the typical rice fields in Asia, over South India, North India, Thailand, and Bangladesh, and so on, so on. And I will show you an example over the lower Ganges basin. This the red line shows the methane concentration by a satellite sensor named Skiyamaki that had measured methane concentration before GOSAT. The emission estimate from rice paddy field is shown here, and the correlation between the observed methane concentration and emission estimate from rice paddies is shown in a normalized scale. You can see the correlation is very good. The satellite, therefore, can detect methane concentration which are really high over the area of intense methane emissions. We now have GOSAT data after 2009, and the observed methane maps are similar to that of Skiyamaki, like this. It's a Skiyamaki map and GOSAT map, and this, the methane spatial distribution is also corresponding to methane emission estimate, like this. Again, you can see a good correlation again among those maps. Very recently, a new finding was reported by NIES and MOE, not only over the rice paddies, in various places over the world. We can see such positive correlations between methane concentration, between methane enhancement expected from emission estimate in abscissa, okay? And the vertical axis shows a GOSAT high methane concentration. So you can see the good correlation, and that means that these findings indicate the potential of GOSAT to detect anthropogenic methane emissions. As I mentioned, we have a large amount of satellite data and ground-based data already. However, to utilize all of the data effectively, we need the help of an efficient database system. Otherwise, we would be blind to a pile of treasure. We should know what kind of data are available, where they are, and how to access to those data. And scientists know their own field very well, but in general, they are not familiar to technical terms of other disciplines. Thus, we need help to understand the technical terms among different disciplines each other. So to answer the request, DIAS, Data Integration and Analysis System, has been developed by Japanese scientists. Now, many scientists from various disciplines are starting to input their data into DIAS. In the field of hydrology, a great amount of the data have been accumulated. Atmospheric data are still at the beginning stage, but DIAS will be a help for all people working on global observation data in the near future. Okay, today I focused on GOSAT and DIAS as Japanese contributions for GIAS. GOSAT has observed carbon dioxide and methane for 6 years, and global budget of carbon dioxide and methane has been improved by using GOSAT. Our next challenge is to downscale the budget estimate to a regional scale. Integration of satellite on-site measurement and model outputs is essentially important, but to utilize all those data effectively, we need a tool to help us. DIAS will be helpful for us to use those data. Finally, I'd like to say the technology at present is limited, but the focus is to improve the technology to meet the needs for green growth. Thank you very much.